Okay, let's get started. Let's get started. How many times do I have to say it? Let's see. Let us get started. Excuse me. Sorry. Oh, hello. Let's start class. Excuse me. Sorry. Okay. Great. Excellent. Okay. So, hello everyone. Welcome back to 3:30. This is lecture 3. I see that attendance has already started to go down, but I won't take it personally. So before we get started, just a bit of admin. So assignment one is out, and it's on my courses. Sorry about the technical issues at the start at 10 a.m., but it's out, and so it'll be due in 2 Thursdays from now. Yeah. Okay, and so today, essentially, we're going to start the actual interesting part of the course, in which we study automata theory, right? So if you remember from lecture 1, automata theory is the study of computational models. And so there's different types of computational models, each with more and more power. They start from deterministic finite automata, which we're going to study today, and they finish with Turing machines, which we'll study after the midterm, okay? Okay, so before we do that, I just wanted to give you a bit of history, because I think it's interesting to do a bit of history just before you do something mathematically rigorous. So first of all, what's actually the meaning of automaton? For our purposes, we take it to mean a theoretical computing machine, right? Which makes sense with what I've been saying for the last 2 lectures. And it comes from the Greek automatos, which means acting of itself. But we're not really going to talk about that aspect of automata, because that's more related to sort of AI fields. Okay. So a bit of history before we actually talk about deterministic finite automata. So this first point is going to be rather familiar, because we talked about it in lecture 1. So in 1937, Alan Turing introduces the A machines. So he introduces these machines in which the A stood for automatic, and he shows that this problem, which I debated whether I would pronounce it in front of you. I think I'll not do that. So this decision procedure problem, which David Hilbert and Wilhelm Ackermann had introduced in 1928, he used the A machines to prove that this was undecidable, right? So he showed that there wasn't any computational model, how sophisticated you want it to be, that could decide, that could create a decision procedure that could solve this decision problem, right? But by 1939, Alan Turing had actually gone back to the UK. He was at Princeton with Alonzo Church. But in 1939, he went back to the UK, and then he started to work for the British government. And he sort of worked on breaking the German encryption machine known as Enigma, which you can find out more about during sort of Claude's cryptography class. There's also a movie called The Imitation Game, which is quite good. And so Alan Turing was kind of out of the picture, and he wasn't really thinking about theoretical computing machines at that moment anymore. And so some people had to sort of take over. And in particular, in 1942, Warren McCulloch, who's actually a brain doctor, and Walter Pitts, who was a logician, introduced the neural network. And they introduced this neural network to model how the brain functions. Okay? And they introduced this in a paper known as A Logical Calculus of the Ideas Immanent in Nervous Activity. Okay? And the whole reason for this paper was that they were trying to understand logical reasoning in people. Okay? And so the idea was that if you had a good model of the brain, then you could possibly understand how humans reason logically. Okay? And that turned out to be true to some extent. Then in 1951, John von Neumann, who's another very famous computer scientist, probably one of the pioneers, along with Turing, publishes a follow-up work to this McCulloch and Pitts paper known as The General and Logical Theory of Automata, in which he actually introduces a computational model. So McCulloch and Pitts were more interested in modeling the brain. Neumann was interested in modeling electrical components and computation. And then lastly, Marvin Minsky sort of took some inspiration from von Neumann and also the McCulloch and Pitts paper, and publishes a book in 1967 known as Finite and Infinite Machines. and that's an excellent segue, that's why I put it there, to talk about finite machines, right? Whoops. Finite machines. Okay. In particular, today's lecture is going to be about deterministic, I don't know why I'm writing it, but deterministic finite machines, or automata. And we'll see in a second why they're called deterministic, but the reason why they're called finite is because they have a finite amount of memory. Okay? So that's the reason why we call them finite. Okay? So let's actually start talking about deterministic finite automata. So now I'm going to switch back to my beautiful handwriting. So I think the first thing I want to do is give you a general high-level idea of what a DFA is, and then we'll look at some concrete examples. Okay? So let me give you an informal definition. So this definition is informal. Okay? So a DFA, which we usually represent with the variable m is for machine, is a computational model which, given some input x, where x belongs to sigma star, where sigma star is the set of all strings over the alphabet sigma, so we're assuming that we have a fixed alphabet. Okay. And so given some input string x, m either accepts or rejects x. Okay? So in other words, DFAs are, that's not mine, so I'll just keep going. DFAs are known as language recognizers or acceptors because given strings, they either accept or reject them. Okay? So DFA are known, known as language acceptors or language recognizers. Okay. So given an input string x, they either accept or reject them. So far, so good? Yeah, okay. Okay, so what's an illustration of this informal idea? So like I said, we're going to do concrete examples in a second, but I think it's good to give you a high-level idea first. So in a DFA-M, which I'm going to represent with this box here. So DFA-M is comprised of a control unit. So this is the control unit. The control unit is what actually executes the computations. And it's also comprised of an input tape. The input tape is what holds the input string. Make sense? Okay, good. So now, given some input, right, x, so x is a string, meaning that it's a sequence of symbols, right? We saw this on Tuesday. Each of these symbols are in the alphabet. What does the machine actually do, right? So I give it some string. What it does is, the first thing it does is it takes the string and it puts it on its input tape. Okay, so it puts x on its input tape, and so it puts A1, A2, A3, all the way to AN on its input tape. And so we can imagine that these are separated by small cells. Okay. And now the control unit actually has to execute some computation. Okay, so how is it going to do that? Well, you can imagine that the DFA is a machine, and so like any machine, you have to sort of wake it up, right? And so for the machine to wake up, it has to get started, and so it starts at the start state, right? So this incoming edge here is the start state. So this is like my laptop waking up after after I've used it. I don't know. After it's been on sleep. Sorry. Okay. Okay. So my control unit is now at the start state, and now what it needs to do is it needs to start reading the string, right? Because the whole point is to read the string and then say whether it accepts or rejects the string. So how does it do that? Well, it's going to read the first symbol, right? The first symbol of the string. It goes from left to right. And so it reads A1, and based on A1, it's going to do something. So maybe if it's at the start, if it's at its start state and it's reading A1, then it goes to some other state. Okay, so we say that it transitions. Okay. So the DFA transitions to some other state. Okay, and so now it's read A1. It's read A1 because it was able to go to another state, and so it moves its pointer to A2, and then it reads A2, and then because now it's in this state, the state given A2 is going to do something else. So maybe it's going to go to this state here. Okay, and then so now I've read A2 and I've transitioned from this state to this state. So now I can move my pointer to A3, and I keep going, right? And so this process keeps going. Maybe at A3, there's a self loop here, and so I remain in the same state. Okay, and then I go to A4, and I keep doing this until I get to the last symbol. Once I'm at the last symbol, this is the before last state I'm in. So I'm in my before last state, and I'm reading the last symbol. Then I read the last symbol based on the state where I am, and I transition to a final state. So this is the final state of the computation. And to know whether the machine accepts or rejects the string depends on what state it ends on, right? So if this state is a normal state, then it's going to reject the string. But if the state is an accept state, and so we usually denote that by a double circle, then it accepts the string. Okay, so in other words, if M ends in an accept state, it accepts X, right? That's why it's called an accept state. Otherwise, it rejects X. Okay? So that's the high-level intuition. Yeah. Yeah. It's normal if you're confused at this point, though. Okay. If you're confused, it's normal because this is a high-level idea. I'll give you a concrete example, and then it'll be clear. Okay? This is a high-level idea. Okay, so now let's look at a concrete example. This was an illustration. Okay? Don't actually put this in your assignment solution. Okay? Okay. So, wait, actually, maybe I shouldn't scroll too fast because you're probably still writing. Okay. So, a concrete example now. Suppose I have the alphabet 0, 1, and I have the following DFA M. Okay, so my DFA is going to be represented concretely using a state transition diagram. And so what that looks like in this case, this is a particular machine, and so I'm going to draw it this way. It's going to have a start state. It's going to have a transition when it reads the symbol 1 to some other state here, which is going to be an accept state. Then this is going to go back with a transition with a label 1, and it's going to have some self loops with label 0. Okay? And just for the sake of nomenclature, let's just call the start state Q0, and this other state, which is an accept state, Q1. Again, it's normal if you're confused at this point. Like, if I were you, I wouldn't know what the heck I was writing. Right? So that's normal. Okay? So this is a DFA M. Okay? Now, how does the DFA do what I said it was going to do? Right? So how does it take an input string and then either accept or reject it? Right? So concretely, let's look at some input string X, which I'll say is 0, 1, 1. Right? This is a valid string because it's using symbols only from sigma. Okay? And so how does my machine M actually go through a computation? So remember, it starts at the start state. That's why it's called the start state. And so it starts at Q0. Yeah? So it starts at Q0, and it's reading a 0. Okay? So if I'm at Q0 and I read a 0, well, I'm going to use this transition, because this is the transition that has a label 0. And so I'll self-loop back to Q0. Right? So I self-loop back to Q0, and I've read 0 now. So that means that I can transition, I can move my pointer, sorry, not transition, I can move my pointer, and now I'm reading 1. Okay? So let me just write that down. I started with my pointer at 0, and I was at state Q0. Now I've read 0, but I've self-looped, right? So I'm still at the same state. I'm still at the same state, but now I've moved my pointer, and my pointer is now on 1. So I'm reading 1, but I'm at state Q0. Okay? Now again, I do the same thing, right? I'm at Q0, but now I'm reading a 1, right? So if I'm reading a 1, well, I'm not going to take this transition because this transition is labeled 0. So instead, I'm going to take a transition, this transition, because it's labeled 1, right? And so then I read this 1, and I move my pointer here. Okay? So what did I just say? I just said that I was at Q0, and I was reading a 1, and so I transitioned to Q1, and I moved my pointer. So now I'm at Q1, right? I'm no longer at Q0. No longer at Q0, I'm at Q1. But now I have as input 1, right? So I read symbol by symbol, right? And so here my symbol that I'm reading is 1. But if I'm at Q1 and I read a 1, then I have to take this transition. So I take this transition and I go back to Q0, right? So I take the transition here and I go back to Q0. And now this is the end of the string, right? So remember, this is the end of string marker. So now I'm at the end of the string, right? I have nothing to read anymore. But I'm in state Q0. Right? Q0 is here. It's not an accept state because it isn't doubly circled. And so that means that I reject X. I reject X because I was given X, right? I went through the computation, and I ended up in a state Q0, which wasn't an accept state. Okay? And so that leads to a reject. Okay? Give me one moment. So then I reject X. Let me just show an example where you accept, and then you can ask a question. Okay? Okay. So this is how you reject a string X. This is how a machine would reject a string X. Now, how could it actually accept a string? So for it to accept a string, I need to actually change the input string, right? So in this case, let it be 1, 0, 0. Okay? So again, I'm going to start at the start state. That's why it's called the start state. And my pointer is at 1. Right? So now I'm at Q0, and I'm reading a 1. I'm not reading a 0 anymore. I'm reading a 1. Because that's what's on my pointer, right? And so if I'm reading a 1 and I'm at Q0, I go to Q1, right? So I transition to Q1, and now I'm reading a 0. Okay? So now I'm at Q1, and I'm reading a 0, so I self-loop, which means that I've read the 0, but I stay in the same state, right? So I've read the 0, so I move my pointer, but I stay in the same state, right? Because it's a self-loop. Okay? And then again, I read another 0, right? And again, the same thing happens, right? And that's not surprising because the machine is deterministic, which means that its moves are uniquely determined by the state it's in and by the symbol it's reading. Okay? And so again, I stay at Q1, but now my pointer is at the end of the string marker. And so now what happens is that my machine ends its computation on Q1. Q1 is an accept state, right? And so that means that X gets accepted. So that means that you accept X, and here I'll write because Q1 is an accept state. Okay, and here you reject X because Q0 is not an accept state. Okay? Now I can take questions. Yes, Marcello. Is it philosophical? Okay. That's a very good question. Excellent. So, yeah, that's a great question. So the question that Marcello just asked is, okay, so this is a very important question. Thank you, Marcello. So I have put the string on my input tape, right? And I've read it from left to right. Now the question was, can I start back here and then go from right to left, right? And so the answer is no, I cannot do that, okay? I can only read from left to right. I can't go back. If I go back, it turns out that's a more powerful computational machine. That's right. That's right. That's right. So this is not a Turing machine, it's a DFA, right? And so a Turing machine is more powerful than a DFA, which is why a DFA can't do that. Okay. Other questions? Yeah? Yeah. You have to tell me what state you're talking about and then what input symbol you're talking about. Q1? Yeah. Sorry, guys, can you, I'm trying to listen to the question. Sorry. Excuse me. Sorry. Could you, sorry. It's really distracting when you whisper. Thank you. Yeah, that's right. That is what you're doing. If you're at Q0 and you read a 0, you stay at Q0. I think we have to take this offline. Come talk to me after. Yeah. Generalized question, yeah. Okay, good. So those are two very good questions. So first of all, a DFA, right, a deterministic finite automaton, is a language acceptor, right? So right now I've shown you that it accepts 2 strings, right? But in general, this DFA is going to accept a set of strings, okay? And so that's going to be the language accepted by the DFA. And I'll talk about that in a second, okay? And then the other question was, what does this state represent, right? And so that's a very good question as well. The idea is that the states of DFAs represent information that the machine has to remember, okay? And so that's a great segue. Hold on to your other questions, but that's a great segue to talk about what this machine is actually doing, okay? Because what's going on is if I'm in Q0, right, and I'm reading zeros, I'm just staying at Q0, yes? The only way I can change state is if I read a 1, right? So if I read a 1, I go from Q0 to Q1, right? And then the same thing in Q1. If I'm at Q1 and I'm reading zeros, right, then I stay in Q1. But if I read a 1, I go back to Q0. So effectively what that means is that I'm keeping track of not exactly the number of ones, but the parity of the number of ones, right? So what that means is I'm keeping track of whether I've seen an even number of ones or an odd number of ones, right? And so to make that super clear, imagine I have an input x is 1, 1. So I have 2 1s, which is even, right? Then I start at Q0. I think that I have an even number of 1s. Now I transition to Q1 because I see a 1. So now it looks like I have an odd number of 1s. But now I read another 1, and so I go back to Q0. So in fact, it actually means that I have an even number of 1s, right? And so that means that Q0 is encoding, so it encodes even number of 1s, and Q1 encodes having an odd number of 1s. And because the only accept state is Q1, which encodes strings that have an odd number of 1s, then that means that the language accepted by M, which is denoted this way, so this is the language accepted by M, it's going to be a language, right? A set of strings. So a set of strings that are formed using the alphabet 0, 1, where x has an odd number of ones. Okay? So this is the language accepted by my machine M. Okay? Is that clear? See, how many people are frowning? Not that many. Good, yeah? Yeah. Yeah, that's right. Yeah. Yeah, absolutely. Yeah, very good question. So if it's x 1, 0, 0, 1, right? Well, let's just work through it. I'm at Q0, I read a 1. Now I'm at Q1, I read 2 zeros. And then I read another 1, I go back to Q0. It's just where you end, right? It's where the machine's computation ends. If it ends in Q1, Q1's an accept state, and so it accepts the string. You do, right? You go back to Q0, which is not an accept state, and so you reject it. Where did I write that? I also think we need to take this offline. Otherwise, we'll, yeah, sorry. Yeah. Yeah, so that's another good question. So these are all good questions that you need to see more examples to talk about. But you can have as many accept states as you want, and as many not accept states as you want. Yeah, we'll see an example of that. Yeah? Yeah. Yeah, so I think the question was, does every state have a purpose, right? And usually, yes. Yeah. Usually, if you're designing a machine and you want to use as few states as possible, then each state is going to be encoding a unique piece of information. Yeah. Yeah. That's right. So it's a deterministic finite automata, and so finite means it has a finite number of states. Yes, excellent. Yeah? Okay. This X? No, this is a, what, how, what, no, what? This is an end of string marker, yes. Oh, that's why people, oh. Okay, if people are confused because of that, this is an end of string marker. Thank you. Okay. Yeah. Yeah. No. I'm extremely certain that this is correct. So if you have like specific questions, please ask me offline, okay? Any general questions? Yeah? I'll take 2 more questions because then we have to move on. Yeah. Those are 2 good questions. So exactly what is transitioning is the state. I'm going from one state to another. The machine is going from one state to another. And how does the machine know what state it's in? It's because it always starts at Q0. This is by definition how this machine works. And so if it knows that it starts at Q0, then it knows exactly how to track itself. Okay? Because everything is uniquely determined. Okay? Okay, one more question. We have to move on. The person behind you. Yeah. No. Yes. No to your first question. There does not have to be an accept state. And yes, a DFA can have a single state. We'll see an example of that at the end of the class. Okay, good. I have to move on. Okay? So this is one example. I'll show you another example, and then maybe you can ask more questions. Okay. So another example. Now, what I did is I gave you a DFA, and then I showed you sort of through some examples what language it accepted. So now I'm going to try to do the other way. I'm going to say, design a DFA M such that the language accepted by M is the set of strings over the alphabet, what did I say, AB, such that W contains the substring AB. Okay? So, in effect, what I'm doing is I'm trying to design a machine that looks for strings which have a contiguous sequence of AB, right? So in other words, if I have a string AAA, then that's no good. There's no AB in there. If I have a string AAB, then that's great because I have an AB there, right? That's what I'm trying to look for. Okay? So how do I design a machine that does this? Well, the idea is to use states that encode information, right? My states need to encode some piece of information. And so when I start at Q0, right, Q0 is going to act as my I haven't seen anything yet, right? So I've seen no strings yet. We'll update this meaning in a second because it's not entirely right. Okay? So I'm at Q0, right? And now if I see a B, well, actually I can just stay at Q0, right? Because what I'm looking for, right, my machine is actively searching for a B, right? So if it sees a B, it doesn't help, right? If it sees a B, it doesn't help, and so it's going to stay at Q0, right? So in other words, Q0 isn't really I've seen no strings yet. It's more like I haven't seen an A. Haven't seen an A. Okay? So if I haven't seen an A yet, I just stay in Q0. But now if I see an A, that means that I'm on the road to getting to AB, right? So that means that I can transition to another state, Q1, where now Q1 is encoding the fact that I've seen an A, right? So it means that I've seen an A. Okay? So I'm at Q1 because I've seen an A, right? Now what I'm doing is I'm looking for a B, right? Because this machine, what it wants to do is it wants to look for AB, right? So then if I'm at Q1 and I see an A, that doesn't really help me because I already know I saw an A, right? And so that's redundant information, so I can just stay in Q1. Okay? But now what happens if I see a B? Well, a B is a winner, right? Because I know I've just seen an A. And now if I've seen a B, that means that I've seen a B, right? If I see a B, then I'm very happy. I go to Q2, and I'm at Q2 an accept state. And once I'm at Q2, I don't care whatever else I see, because I know I've seen an A and a B. I've seen AB. And so I can just stay in Q2, because whatever I see after that is going to be accepted as well. Okay? So Q2 encodes the information that now I've seen AB. Is that clear? Yeah, question? Yes, very good question. Excellent question. So the short answer is yes. And the reason why, so the question was, for each state, right? So here I have an alphabet AB. And so the question was, for each state, do I have to have a transition for B and a transition for A? And the answer to that is yes, right? It's yes because this machine is deterministic. So it needs to know what to do at every single possible state, right? It can't guess. It can't be like, oh, I don't know, right? It has to be determined uniquely, okay? So, exactly, yeah, right, exactly. Good, yeah, precisely, yeah. So now you see why we talked about finite alphabets, right? Okay, so maybe I'll just write a note here, is that for each state, there are exactly cardinality of sigma transitions, one transition for each letter. I'm using small sigma for a letter in the alphabet. Okay? Okay. Yeah. Oh, yeah. You'll see, yeah. Next example. You don't always need a self loop. Yeah. That was the question, right? Oh, no, don't do that. No, in a DFA, you have to have, so in this case, my alphabet is AB. And so every state has to have 2 transitions, one for A, one for B. Don't skip any transitions. Yeah. Yeah. Accept state, not final state. Accept state. Yeah, so it looks for the first AB, right? It's seen the first AB, so now it's happy, right? So whatever it sees after, it's okay, because that string already has AB. I'm not sure I understand the question. Reach the first set, and then I didn't hear the rest. Break the process? No, why do you want to break? We need to take this offline again, sorry. Because these are very specific questions, I can't just answer them. Okay, please ask me after. I'd be, to everyone who I said, please take this offline, I'm serious, just come talk to me after, and I'll be happy to spend an hour talking to you, okay? But I have to keep the class moving. I'll do another example, because I'm already running behind, of course, because that's, I guess, my thing. I'll do another example, and hopefully things get even more clear, okay? Okay, so again, it's going to be a question about designing a DFA, but now it's going to be design a DFA M such that the language accepted by M is AB power n, where n is greater or equal to 0. Right? So we've seen this notation Tuesday. So just a reminder, that notation means, right, so AB n means you're writing AB n times, right? And so this set is equal to the empty string AB, 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 well, I think you get the point, and so on, right? Notice that it has the empty string, right? It has the empty string because AB0 is by definition the empty string, okay? Okay, good. I see that some people are trying to work it out, so that's nice. Okay, so how am I going to do this? It's going to be the same idea, but now I'm going to try to show you a different sort of design technique. Okay? And this different design technique is more like, let's start with the skeleton of the machine and then sort of complete it. Okay? So what do I mean by that? So I know that what I'm doing is I'm trying to search for ABs, ABs, right? And so that means that in my machine, I need to have some kind of sort of cycle where I'm going to A, and then I'm going back to B, right? So in other words, I need a cycle of 2 states where from one state to another, I'm reading an A. From that state back to the other state, I'm reading a B. Okay? So that's very wordy. What does that actually look like? It means that I'm looking for an A and then a B, right? So I'm just looking for ABs, 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 right? And so if I'm just looking for ABs, ABs, then in this case, my accept state is going to be the start state, right? And this DFA isn't complete yet, right? So this is like the first step in designing this DFA. But let's just check that already this kind of works. So if I have the empty string, then my DFA is going to start at the start state, and then it has nothing to read. If it has nothing to read, it's just going to stop at the start state. But in this case, the start state is an accept state, and so it's going to accept the empty string. Okay. Next, if I have AB, then my machine is going to start here, it's going to read an A, and then it's going to read a B, and it's going to end back at the start state, which is an accept state, and so it's going to accept AB. Okay. And the same thing for, say, AB, AB. It's going to read an A, read a B, read an A, read a B, and so it ends in this start state, which is, again, an accept state, and so it's going to accept AB, AB. Right? So it seems like I've dealt with all the cases where I need to accept strings. So now what I need to do is I need to sort of fill out this DFA so that I can deal with the negative cases. Okay. So for instance, the shortest string that's a negative case is, well, either A or B. So I know that A is going to get rejected because it's just going to go here, and then this machine has as this state not an accept state, so this isn't an accept state, and so A is going to be rejected. But now if I see a B, right, immediately if I see a B, that means that there's no chance for me to see ABs, right? Because I've started with B. And so starting with B means that I can immediately reject anything else I see. So that means that if I'm in the start state and I read a B, then I'm going to go to this state, which I'm going to call the dead state. So you can think of the dead state as kind of like this black hole or this like garbage collector. Okay? It just takes all the states that are no good. Right? And so because all these states are rejected, then it's going to have a self loop with A and B. So now the only other transition I'm missing is the one here, and it's the one for A, right? So in other words, it's if I start here and I read an A and then I read another A, what should happen? Well, that means that I've read 2 consecutive A's. And so again, there isn't a chance for me to see only ABs, right? Because I've seen 2 A's, right? So if I've seen 2 A's in a row, then I can't possibly have seen A's and B's and A's and B's. And so again, that means that from here, I'm going to have to reject. Okay? And so I just send that to this sort of garbage collector state. Okay? Does this make sense? We're confused. Okay, blank faces. I don't know what that means. Can't read blank faces. Yeah? Yeah. Yeah, outgoing, yeah, exactly. Yeah, outgoing transitions have, yeah, exactly, yeah. Yeah. Oh, that's a good question. That's a very good question. The question was, are all states connected to the start state, right? That's a sort of a rephrasing of the question. And the answer is no, not necessarily. You could have, say, some state here, right? Maybe this is a machine, and you have some state here, but this state is useless, right? It's a useless state because it's unreachable, right? You can never start here. You can never start here and get to here, right? Because there's no transition to it. Right? But this is still a valid DFA. So we're going to look at a formal definition in a second, and then that should answer some of the specifics. Yeah. Self loop here? Oh, self loop here. Okay, that's actually a very good question. So not that the other questions weren't very good. This one is particularly good. So the question was, why can't we just put a self loop on this A here? Okay? And so the reason for that is because you would still accept these strings, but then you would also accept other strings which you shouldn't accept, right? So for instance, you would accept a string A, B, right? Why would you accept that string? Because you would do A, B, right? And that's no good, right? So the machine has to accept ABN and only ABN. Okay, so that was a very good question. Yeah. There can't be any false negatives, and there can't be any false positives. Yeah? Oh, yes, there's several possibilities. Right. So the question is, what are the criteria? Well, in general, there isn't one specific DFA for a given language, right? You can build several different DFAs that all accept the same language, okay? But we'll see in a few lectures that there's this concept of a minimal DFA, and that's a DFA that can't be reduced further. But for tricks in terms of design, that's really honestly just practice. Correct. Yeah, that's right. If it accepts the strings and only those strings. You can have as many states as you want as long as you have a finite number of states. Yeah. 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 I'm going to get to that. That's an excellent question. So the question was, how do you show correctness? Maybe I won't. No, we'll see. I'd like to. It's a proof by induction. We'll try to do it at the end of the class. Yeah. Like, what's the use case of this? Oh, yeah. Some of these are actually quite useful. Like, for instance, in this DFA here, this is a parity checker, right? And so parity checks are very useful in computer networks because you use a parity bit to check whether your message has been corrupted or not. So these are quite useful. Yeah. And they're actually quite efficient. Yeah, last question. Yeah. Yeah. We'll see the proof by induction. Yeah, but that's not rigorous. Okay. Okay. It's really hard to know if people are confused by looking at your faces. At least on Zoom. Well, actually, on Zoom it was worse. I think it's okay. If you have more questions, okay, one nod. Okay, thank God. Okay. So, if you have more questions, please do ask me, okay, after class. So, now that we've looked at examples, what I'd like to do is give you a formal definition of a DFA. Right, so formally, okay. So the definition of a DFA is the following. A DFA M is a 5-tuple where the elements of that tuple are Q, sigma, delta, S0, and F, where Q is the set of states of the machine. Okay. So in other words, these are the possible sort of nodes. Sigma is the input alphabet. Okay, so that's, in other words, what the machine can sort of accept as input. Then delta is the transition function. So it's a function, right? And so that means it takes inputs and it produces an output. In this case, delta takes a state and a symbol, and it returns a state. Right? So in other words, that's the thing that's telling you how to transition from one state to another. Right? So for instance, if I have the state Q and the state P, and to go from Q to P, I can read an A, then that's equivalent to saying that delta Q of A is equal to P. Okay. Then S0 or S0 is the start state, where it's just an element of Q. Okay. So that's where the machine starts its computation. And then finally F. F is a poor choice of variable because it doesn't stand for final states, it stands for accept states. And it's just a collection of states that are accept states. Right, so in other words, it's the states with double circles. Okay? So, for instance, this was the previous machine. Let me just clean it up a bit. Right. So this was my machine M, right? But I can also describe M formally, where I say that Q, if I name these states, so let's say this is Q0, this is Q1, and this is Q2, then I say that the set of states is Q0, Q1, Q2. The input alphabet is clearly AB. The transition function, I'm not going to write it out, but basically it'd be a 3x2 table, right? You have 3 states, and you have 2 letters in the alphabet, and so each one is telling you where to go if you're in that state and you're reading that letter of the alphabet. But for instance, if I'm at Q0 and I read an A, then that leads me to Q1. Okay? And then S0, or the start state, is Q0, right? Because it's the one with the incoming arrow. And then lastly, F, the set of accept states. In this case, the only state with a double circle is this guy. So that means that F is the set containing Q0. Okay. So this is how you describe DFAs formally. Yeah? Drawing. Please draw in the assignments. Please use your artistic creativity. You can use your you can use your iPad and just submit a PDF. Yeah. It can be hand drawn. Yes, that's why I said use your artistic abilities. Yeah, don't insert. Yeah, but you can convert a JPEG to a PDF. Okay, let's talk about this after, please. Okay. Okay. Good? All right. So that's the formal definition of a DFA. The other thing I need to show you is the formal definition of how you can accept a string. Because so far, intuitively, what we've been saying is you accept a string if you start at the start state, and then you can somehow get back to an accept state. In this case, the only accept state was this guy. But in general, right, in general, given a DFA M, right, so this is some machine M, it has a start state, it has some accept states. To accept a string X, right, to accept X, if M reads X, then it has to be able to get to an accept state, right? That's what acceptance means for a DFA. And so I need to formally define that for you. Okay, so how do we formally define? Formally, we need to talk about the extended transition function. Which I'll call delta superscript star, right? So the extended transition function is a function, it's related to the transition function, but instead of taking a state, well, actually, no, it takes a state, but instead of taking a symbol, it takes a string, and then it returns a state, right? And so, in other words, it's a generalization of the transition function to strings, right? So, for instance, if I have some machine, and I have a state P, and then I have some intermediate states, right? And maybe I have a connection like this, and I have like A, B, A, right? Then what the extended transition function is able to do, it's able to say, if I'm at P and I read ABA, right, so the whole string, then I know that I'm going to end up at S, right? Because I'll take this A to go to P, to Q, this B to go to R, and this A to go to S. Okay? And so this is what the extended transition function allows me to do. It allows me to talk about strings, which I need to do to talk about the language accepted by the machine. Okay? And so the formal definition for this is by induction. And when I say by induction, I mean we define this inductively or recursively. So the formal definition is, so let's say the definition of delta star is, so the base case is if you're in a state Q and you read the empty string, then you just stay at Q, right? So that makes sense, right? If you're a machine and you're at a state and you're not reading a symbol, you're just reading the empty string, then you just stay there. You stay at your state. The recursive case is what happens when I have a string W and a symbol A, and I'm at state Q and I'm reading WA, right? So the intuition here is for the base case, I was at Q and I was reading the empty string, so I would just stay at Q. But for the second case, I'm at Q, and I read W, right? And then I get to a state, and then I read A, and then I get to another state, right? So reading WA directly is the same thing as first reading W and then reading A. Okay? And so that means that delta star QWA is equal to first reading W, right? So this gets me to one state, because remember, delta star returns a state. And then from that state, I read a single symbol. So this is the definition, right? But I'm just giving you the intuition of the definition. Okay? And so then, if we want to talk about acceptance formally, right? Then if we say, given a string X, which is in sigma star, and a DFA M, then we say M accepts X if and only if. So who can complete this if and only if? Yeah. In the accept states. Yeah, excellent. Very good. Excellent. Very good. So it's an if and only if, where the then condition is you start at the start state, you read X, and you end up in a final state, or an accept state, sorry. Right? So the machine accepts a string if and only if the machine starts at the start state, reads the string X, and then ends in an accept state. Right? That's what this definition is telling us. Okay. Right? Yeah, give me a second. And so visually, that just means that you start at Q0, or suppose Q0 is the start state, then you read X, and then reading at X lands you in an accept state. Yeah? Yeah, absolutely, F is a set, by definition. Right? By definition, it's a subset of Q. So it's a set. Absolutely. Yeah. Except states. So maybe I'll specify this. Set of. Yeah. Yeah. Because Q is finite. You have a finite number of states, so you have a finite number of accept states, because F is a subset of Q. Absolutely, yeah. Sure. Yeah. Whatever you want. Yeah, yeah, yeah. Okay. Yeah. That's right. Absolutely. No, they're all equally important. So the question was, it seems like the formal definition of the DFA is silly. Why don't we just use delta star? You need all of the other parts of the definition for delta star to work. So everything's important. Okay. Any questions about this? No. Yeah. Could be the English alphabet, right? English alphabet, 26 letters, last time I checked. That could still be useful if you want to check if you're using sort of some very quick spell checker. Then you could implement a very quick spell checker using DFAs. Yeah. Could still be useful. Yeah. Yeah. I'm not quite sure I understand the question. Are you saying, are there cases where DFAs are useless? Not when they're on the midterm. Okay. Good. Okay. So the last thing I want to do is now define formally the concept of language accepted by a DFA, right? So the language accepted by a DFA is just all of the strings that satisfy this condition, right? So given a DFA M and just given a DFA M, we define the language accepted by the machine M as the set of strings over the input alphabet, such that when you start at the start state and you read an X, then you end up in a final state, right? So here I'm defining M as Q, sigma, delta, S naught, F, right? So I'm using all of the pieces of the definition in this guy, right? So this is the language accepted by M. Okay, good. And so now that we have this nice piece of information, I can talk about the very first class of languages, okay? Because it turns out that languages are sets of strings, and some of these sets of strings are very easy to accept. It's very easy to create a DFA that accepts them. Others are very tricky, and others are sort of impossible, right? So there's some languages where there doesn't exist a DFA that accepts them. But for the languages that do have a DFA that accepts them, they have a special name, which is regular. Okay, and so I'll define this here. Given some alphabet sigma and some language which is a subset of sigma star, L is regular if there exists a DFA M such that the language accepted by M is L. Okay. So all of the languages that are accepted by DFAs are regular, and all regular languages have DFAs that accept them. Okay? Okay. So, and the idea of the first part of the class is that we're going to see that there are sort of different levels, different classes of languages. So regular languages are the simplest class of languages. Then we'll talk about context-free languages. Context-free languages. And then outside of that, we'll talk about decidable versus undecidable languages. So I'll just write here, decidable languages which are related to Turing machines. Okay? Okay. So now what I'd like to do is I'd like to show you a proof of correctness for a machine, because that's also in your assignment. So the idea is, if you want to prove that a language is regular, right, you need to first show that there's a DFA that accepts it, right? So in other words, you have to create a DFA that accepts L, but then you also have to show the correctness of the machine, right? And so this is going to be a proof technique. How do we prove that a language L is regular? Okay. Well, the first thing we need to do, is construct a DFA for it. Construct a DFA M such that the language accepted by M is equal to L. Right? And the second thing you need to do for this proof to be correct is you need to prove the correctness of your machine. Right? And so you need to prove the correctness of M. And so to do that, right, in other words, you need to show that for every string X in sigma star, X is in the language accepted by M if and only if X is in L. Right? And so every string that gets accepted by the machine has to be in L, and every string in L has to be accepted by the machine. And so I'll show you how to do this in a second. But let me give you the, okay, no, I'll start with an example. Yeah, okay. So the example here is prove that the language L, which is equal to ABN for n greater or equal to 0, is regular. And so I have, of course, purposely chosen a language for which we've already designed a DFA for. Otherwise, I wouldn't have time to finish this example. And so magically, it appears here. Oh, that was cool. Okay, so that's the machine that accepts L, right? Now what I need to do is I need to prove, right, so this is M. I need to prove that L of M is equal to L. And so to do that, let me just relabel these states. I forgot to do that. Okay. And so what's the proof technique to do this? To do this very rigorously, the first thing you need to do is you need to make a claim about the extended transition function delta star, and prove that claim. And the second thing you need to do is you need to show, using the first step, that for any string x in sigma star, x is in L of M, if and only if x is in L. Okay? So that's how you need to do that. Of course, it's very normal that you don't know what either of these two statements means. I have to show you an example. Can it wait? Oh, yeah. Oh, thank you, actually. It was very quick. Thank you for being honest and for that correction. Okay, good. Excellent. So what do what do both of these statements mean? Let me actually show you how to do this. Okay. So for the first statement, right, for making a claim about the transition function, right, this claim needs to essentially say what intuitively you think your machine is doing. And so to do that, you need to say what each of your states are doing. Okay? So one, it has to be a claim about what each state is responsible for. So what is each state doing? Okay. Well, in this case, hopefully it's relatively easy because we've already talked about it. So my statement is going to depend on the machine and some string, right? And it's going to say the following. It's going to say that if I have a string, right, if I have an input string, and I read that string and it ends in Q0, then that means that my string has a form ABN. Okay, so that's going to be the first part of the statement. I'm going to say if I'm at Q0 and I read a string and I end in Q0, then that means that my string has the form ABN for n greater or equal to 0. So that's the first part of the statement. This statement is going to be a sequences of if-thens, where each conditional in the if is going to say, well, I'm in this state, and then the then is going to be, what is the claim about W when I'm in that state? So this is the first if-then, and it's going to be conjoined with an and, with another statement about what happens if I'm in Q1. So if I'm in Q1, if I started reading from Q0 and I end in Q1, then what does that mean, right? What does W look like? Well, if we go back to the machine, I know that Q0 is encoding AB, right? Sequences of ABs, right? So A's and B's and A's and B's. But now if I end in Q1, that means that I have A's and B's, right? But then I have one lingering A. So I have a final A, which, because there isn't a B, I have to stay in Q1. So what that looks like is that I'll have W looks like ABN, and then followed by an A, right, for some n greater or equal to 0. And the last piece of the statement is what happens if I'm in Q2. Then what does W look like? In this case, because Q2 is actually a sort of garbage collector state, it's a dead state, I can just say that W looks like neither Q1 nor Q2. Okay? And that's going to work just fine for the proof. Then W does not look like ABN, nor does it look like ABNA for any n greater or equal to 0. Okay? And this is going to be the statement that I'm going to want to prove. Right? So this is the statement that I'm going to use to show the correctness of my machine. Now, this statement is just a statement I sort of wrote down. It doesn't have a proof, so I need to prove it. Because I won't have time to do that, I'm going to skip the proof and post the notes for it. But the proof is going to be by induction on the length of W. And so please actually do make sure you read this proof. It's quite important. So this is the statement. Now, to know that my statement works, actually it's going to be nice to use it to validate that my machine is in fact correct. Okay, and so that's the second step. I need to now show, right? I want to show that given a DFA M, that every x in sigma star, that for every x in sigma star, x is in L of M, if and only if x is in L. Okay? And so this is an if and only if, right? So I need to prove both directions, right? I need to prove the if then and the then if, right? And so to do that, for the first direction, I'm going to prove this directly. And for the other direction, I'm going to use the contrapositive. And if you're confused about this part of the lecture, that's okay. Please just reread this part, and I think it'll be clear. And also just ask me questions. But this part is slightly more advanced. Okay, so it's normal if you're a bit confused. So how am I going to prove this directly, right? Well, what I need to show, right, I need to show if I have some string x in L of M, then that string also has to be in L, right? So how I'm going to do that? Well, let's just pick some string x in sigma star and say that x is in L of M. And so by definition, what does it mean for x to be in L of M? Any takers for that question? Yeah? Not quite. If, in general, for any machine, if I say that x is in L of M, that just means that I know that if you start at Q0 and you read that string, you end in a final state, or an accept state, right? And so what that directly implies is that if I start at the start state and I read x, then I end in a final state. Okay? So let me just make sure I'm using M is Q sigma delta S naught and F. Okay? Right? So now, what does this mean? Right? Remember, the machine looks like this, right? And so if my machine looks like this, and this is Q0, this is Q1, and this is Q2, because I'm saying that the machine belongs to the set of accept states, and the set of accept states in this case is only Q0, then what this implies, it implies that delta star S naught x is in the set containing Q0, right? That's just by replacement. And then directly, because there's only a single element in my state, then I know that S naught x is equal to, is equal to Q0. No, that's fine, that's fine. Okay, so now, right, now I'm going to be able to actually use the statement, right? Remember, my statement here was this guy. This was my statement. And so what my statement says is that if I start at Q0 and I read W, I read some string W, and I end in Q0, right? So if this is true, then my string looks like ABN, right? And so I can then directly use my statement. And so then directly by PMW, that means that X looks like ABN for some n greater or equal to 0. Right? Yeah, okay, we're not good. Okay, so if X looks like ABN, right, the definition of the language L is all the strings that do look like ABN. And so by definition, that means that X is an L. And that shows the first direction. Okay? Yeah? Yeah, let me fix that after class. But I'm just saying, you start at the start state and you read the X and then you end in the start state. I'll just make sure the notation is correct when I look at the notes after. Yeah. Okay, good. So now the other thing I need to show is I need to show the other direction, right? So I showed this direction. Now I need to show this direction. Bless you. And so to do that, right, like I said, I'm going to use the contrapositive. So what does the contrapositive mean? It means that what I'm trying to show, right, what I'm trying to show is if X is in L, then X is in L of M. But now instead, I'm going to use the contrapositive, which is logically equivalent to this statement. And that's going to be if X is not in L of M, then it implies that X is not in L, right? So this is what I'm actually going to try to prove. And so how do I do that? Well, again, I'm going to start with some X in sigma star. And I'm going to say that now X is not in L of M, right? So if X is not in L of M, that means that if I start at the start state and I read X, then I do not end in an accept state, right? And so what that means is if I don't end in an accept state, I end in any of the other states, right? So in this case, any of the other states is either Q1 or Q2, right? It's either Q1 or Q2 because this is an accept state, right? It has a double circle. But this is not an accept state, and neither is this, right? Because it doesn't have a double circle. So that must mean that this guy is in either Q1 or in Q2. Okay? So now that means that either if I start at the start state and I read X, I get Q1, or if I start at the start state and I read an X, I get Q2. So now again, I can use my statement PMW. Right? So again, by PMW, what does this imply? Let me just scroll up for 2 seconds, right? What I've just shown is I've shown that either this is true or this is true, right? And so if either of these two things are true, that means that either this is true or this is true. So in other words, that means that either X looks like ABNA or X does not look like ABNA, nor does it look like ABNA, right? So in other words, it looks like something completely different. And so in either of these two cases, right, by definition of L, right, remember that the definition of L was ABN for some n greater or equal to 0. By definition, that means that n cannot possibly be in L. Right? So that means that X cannot be in L. And so that shows, right, so then this shows that if X is not in L of M, then X is not in L. And so what we've done effectively is we've proven both directions of the equivalence of the if and only if. And so, therefore, for every X in sigma star, X is in L of M, if and only if X is an L. Okay? And so just before I let you go, this process is exactly what I want you to do for assignment 1, question 4, parts 2 and 3. Okay? Yeah. Let's talk after. Well, I'll fix the notes after. Yeah. I do. Yeah, I have office hours right after in case you want to ask me questions. Thank you. See you Tuesday. Yeah. Messed up the notation. Yeah, I'll fix it.
Not bright enough. I actually was going to ask the same thing.